Our solar system is a busy place. It's filled with planets, moons, asteroids, and comets. Each planet follows its own path around the sun. They're like cosmic dancers in a grand ballet. For centuries, we thought we knew the main performers. We knew Mercury, Venus, Earth, Mars, Jupiter, and Saturn. In 1781, an astronomer named William Herschel was looking at the sky. He wasn't a professional scientist at first. He was actually a musician who loved to build his own telescopes. One night he spotted something strange. It was a faint disk of light. At first he thought it was a comet or a star. Most planets in our solar system spin like tops. Imagine Earth. It has a north pole and a south pole, and it spins around an imaginary line connecting these two poles. Other planets have tilts too. Mars has a tilt similar to Earth's. Even the giant Jupiter is tilted, but only by a tiny 3 degrees. Uranus, however, is completely different. It doesn't spin like a top. It rolls like a ball. Its axis is tilted by a staggering 98 degrees. This means the planet is lying on its side as it orbits the sun. Its poles are pointed almost directly towards the sun at certain points in its orbit. To understand why Uranus is so strange, we first need to know where it lives. Our solar system has an order, a clear structure. Uranus is the next planet out from the sun. It is the 7th planet in our cosmic lineup. This places it in the cold, dark, and lonely outer reaches of the solar system. Uranus orbits the sun at an immense distance. On average, it's about 2.9 billion kilometers away. That is roughly 20 times further from the sun than Earth is. Light from our star, which takes just 8 minutes to reach us, takes over 2.5 hours to travel to Uranus. So what is an ice giant exactly? The name can be a little misleading. It doesn't mean Uranus is a solid ball of ice. Instead, it refers to the materials that make up most of the planet. The atmosphere is primarily made of hydrogen and helium, but it is also laced with other chemicals, most notably methane gas. This methane is crucial to Uranus's appearance. In terms of size, Uranus is a true giant compared to Earth. It's about 4 times wider than our planet. It's so big that you could fit about 63 Earths inside it. Despite its enormous volume, it's not as massive as you might think. This is because it's made of lighter materials, like those ices and gases, rather than dense rock and metal. When we compare Uranus to its planetary neighbors, its uniqueness becomes even more striking. Jupiter and Saturn are the kings of the solar system, massive and powerful. Uranus, by contrast, looks almost featureless. Its atmosphere appears as a placid, uniform blue haze. For a long time, astronomers called it the boring planet. But these weather systems are hidden deep beneath the upper layers of methane haze. The winds on Uranus are incredibly fast, reaching speeds of up to 900 kilometers per hour. Now let's look at its sibling, Neptune. Both are ice giants, similar in size and composition, but Neptune is a much more vibrant and dynamic world. To truly grasp how strange Uranus is, we need to talk about something called an axial tilt. Think of it like a planet's posture. Every planet that spins has an imaginary pole running through its center. Earth's axial tilt is about 23.5 degrees. This might not sound like much, but it is the reason we have seasons. Uranus's axial tilt is not 23 degrees or 3 degrees. It is a mind-boggling 98 degrees. This is more than a simple lean. The planet has been completely knocked over. Technically, a tilt of 98 degrees means it is tilted past the horizontal and is even spinning slightly backwards, a phenomenon known as retrograde rotation. So what does it actually mean for a planet to spin on its side? Because it is lying on its side, its poles are not at the top and bottom of the planet. Instead, one pole points towards the sun for a huge part of its orbit. A day on Uranus, the time it takes to complete one full rotation on its axis, is about 17 hours and 14 minutes. This is shorter than an Earth day. For a huge portion of the 84-year orbit, the sun would never set. It would just circle high in the sky for decades. You would be living in one continuous 42-year-long day. Now imagine being at the other pole. For those same 42 years, you would be plunged into a profound and unrelenting darkness. You would experience a single night that lasts for almost half a century. The 98-degree tilt of Uranus means it has the most extreme seasons in the entire solar system. This creates a massive temperature difference between the sunlit side and the dark side. However, When the Voyager 2 spacecraft flew past Uranus in 1986, it saw something completely different. Scientists expected to see a dynamic, churning atmosphere. Instead, they saw a calm, almost featureless pale blue ball. There were no giant storms or dramatic cloud bands. The planet looked strangely serene. The answer, scientists now believe, lies deep within the planet. Uranus lacks a strong internal heat source. Unlike Jupiter or Neptune, it doesn't have a hot core churning out energy. So, we have a planet lying on its side. The big question, the one that has kept astronomers scratching their heads for decades, is simply, why? What could possibly have happened to knock it over so completely? This is a genuine cosmic mystery. It's like arriving at the scene of a cosmic crime. The evidence is right there. But the event happened billions of years ago. The answer tells us a story about the early days of our solar system. It hints at a time when the solar system was a cosmic shooting gallery, with giant objects careening through space and crashing into each other. Scientists have become detectives, proposing different theories to explain the evidence. They range from a single cataclysmic event to a more gradual series of smaller shoves. The most famous and long-standing theory for Uranus's tilt is called the giant impact hypothesis. This theory proposes that very early in its history, when Uranus was still a young, forming planet, it was struck by another enormous object. This was no mere asteroid. The impactor would have been a planet-sized body, perhaps as large as Earth itself or even larger. According to this idea, the impact did not happen head-on. It was a glancing blow, hitting the planet at an angle. This off-center strike delivered a massive amount of rotational energy. The sheer force of this collision was enough to physically knock the entire planet over, tilting its axis of rotation from an upright position to its current sideways orientation. Because of the problems with the single impact model, some scientists started to explore a different idea. What if it wasn't one giant blow that knocked Uranus over? What if instead it was a series of smaller pushes? Each hit would have nudged the planet a little more, gradually increasing its tilt. This death by 1,000 cuts approach has some advantages. A series of smaller impacts might be more statistically likely than one perfectly aimed giant collision. The early solar system was a crowded place, filled with countless protoplanets and large rocky bodies. The multiple impact model might also do a better job of explaining Uranus's moons and ring system. A series of smaller hits would be less disruptive than one giant cataclysm. There is another, more recent theory that takes a completely different approach. This idea suggests that no impact was needed at all. Instead, it proposes that Uranus's tilt could be a result of gravitational resonance. This theory is rooted in the NICE model, a leading hypothesis for how the solar system evolved. The NICE model suggests that the giant planets did not form in their current orbits. Think of pushing a child on a swing. If you time your pushes just right, you can make the swing go higher and higher. In this scenario, the gentle but persistent gravitational tugs from a migrating Neptune could have rocked Uranus's axis. Over millions of years, this steady rocking could have amplified its natural wobble, pushing its tilt further and further until it eventually flopped over onto its side. For a long time, our best view of Uranus came from Voyager 2's brief visit, but technology never stands still. The Hubble Space Telescope has been able to watch Uranus for many years. It has tracked the planet through its long seasons, seeing changes that Voyager 2 missed. These new eyes showed us that Uranus was not so boring after all. Even more recently, the James Webb Space Telescope has turned its powerful infrared gaze towards Uranus. This allows it to peer deeper into Uranus's hazy atmosphere than ever before. It can see the planet's faint, dusty rings with stunning clarity, and even spot some of its small, dim moons. These new tools are revolutionizing our understanding of this distant world. New telescopes are not the only source of fresh clues. When Voyager 2 flew past Uranus, it detected something strange about the planet's magnetic field. But Uranus's magnetic field is a complete mess. It is tilted by a whopping 59 degrees from its spin axis, and it is not even centered on the planet's core. It is offset by about 1/3 of the planet's radius. A new study led by researcher Jacob Kegereis from Durham University suggests that a glancing blow from an icy impactor, perhaps twice the mass of Earth, could do the trick. His simulations showed that such an impact would not only knock Uranus over, but would also create a thin disk of icy debris and gas around the planet's new tilted equator. Modern science isn't just about looking through telescopes, it's also about building virtual worlds inside computers. Supercomputer simulations have become one of the most powerful tools for solving cosmic mysteries. Scientists can input the laws of physics, create a virtual young Uranus, and hurl digital planetoids at it. They can run a scenario over and over again, changing the parameters to see what happens. The latest simulations show that a giant impact from an object made mostly of ice is the most likely culprit. An icy impactor would have vaporized on contact, creating a huge cloud of gas and debris. This disk would then form the moons. It's a detailed, step-by-step account of a planetary catastrophe. The giant impact theory is now emerging as the frontrunner. As powerful new telescopes watch Uranus evolve, they have revealed a surprising turn of events. The boring planet is getting stormy. As the planet moved towards its 2007 equinox, scientists saw a dramatic change. The calm, featureless blue ball began to sprout massive bright clouds. Some of these storm systems were as large as continents on Earth. This was a side of Uranus we had never seen before. This discovery was a revelation. For decades, as the southern hemisphere was heated by the sun, the energy was being stored up deep in the atmosphere. Now that stored energy is being released. These storms also help us understand the planet's composition. The highest, brightest clouds are likely crystals of methane ice, frozen solid in the frigid upper atmosphere. The story of Uranus is more than just a cosmic curiosity. It serves as a natural laboratory for testing our understanding of how planets work. By studying this extreme case, scientists can push their models to their absolute limits. Studying the extreme seasons on Uranus helps us separate the effects of solar heating from a planet's internal heat. Uranus, with its very weak internal heat, is different. This unique situation teaches us about atmospheric physics in a profound way. The discovery that Uranus's atmosphere can store up solar energy for decades was a complete surprise. The strange weather patterns on Uranus force us to think outside the box. These paradoxes challenge our fundamental assumptions about how planetary atmospheres work. The lessons we learn from Uranus extend far beyond the planet itself. The leading theory for its tilt, a giant impact, is a stark reminder that the early solar system was a violent and chaotic place. The sideways spin of Uranus is like a fossilized scar from this turbulent era. This story of a violent past is not unique to Uranus. Our own moon is also thought to have been formed from a giant impact. Understanding Uranus is also crucial for our search for life elsewhere in the universe. When we look for habitable exoplanets, we often focus on their distance from their star, the so-called habitable zone. As we discover more and more exoplanets, we are finding that ice giants may be one of the most common types of planets in the galaxy. Uranus is our closest and best example of such a world. The study of Uranus highlights a significant gap in our exploration of the solar system. While the inner planets and gas giants have been visited multiple times, the ice giants remain largely unexplored. Our entire close-up knowledge of Uranus comes from that single brief flyby of Voyager 2 back in 1986. This makes the ice giants the last true frontier of planetary exploration. Scientists around the world are now advocating for a dedicated mission to Uranus. A modern orbiter, equipped with the latest scientific instruments, could revolutionize our understanding. Such a mission could definitively answer the question of why Uranus is so different from Neptune and solve the mystery of its lack of internal heat. It would be a journey to a completely new type of world. We have journeyed to the cold, distant edge of our solar system. We have met Uranus, the pale blue giant that rolls on its side. We have explored its strange, extreme seasons and delved into the deep past. The evidence, pieced together from fleeting flybys and powerful new telescopes, increasingly points towards a single, violent impact. This story of a cosmic collision is a powerful one, yet science is never truly settled. A new observation, a more powerful simulation, or a future space probe could always reveal a new clue that changes the entire story. Uranus remains an enduring enigma. It is a planet of paradoxes. It has the most extreme seasons in the solar system, yet for a long time it appeared placid and featureless. These mysteries remind us that even in our own cosmic backyard, there are worlds that challenge our theories. The quest to understand Uranus is about more than just solving a single planet's puzzle. It is about understanding our own origins. The story of Uranus's violent past is a chapter in the larger story of our solar system's formation. As we continue to watch, to simulate, and to plan for our return, this tilted giant will undoubtedly have more shocking truths to reveal, each one helping us to better understand the grand cosmic story of which we are all a part.